My name is Nina Ritter Nielsen, and I'll be hosting this event on behalf of the LeBit Consortium. Today we will have 5 talks, 1 from the LeBit coordinator, and 4 from the end users of LeBit, so companies which has already used the LeBit services. We will also have 3 workout rooms where you'll be able to network with experts in the LeBit Consortium. I'll come back to this, but this will be held in another platform called Wonder, which will not be recorded. So only the people you're talking to in a specific circle will know what you talk about, while this Zoom part will be recorded. I'll go through the agenda. The first talk will be Zachary J. Davis, the coordinator from LeBit. He will talk about the LeBit services and the pilot lines, as well as the open call. Then we'll have the 4 presentations from the companies. The first one will be about intelligent packaging and will be held by Alejandro Rodriguez. The second one is about embedded IoT component for construction sectors. Araceli Galvez Moreno from Acciona will give this presentation. The third presentation from the end users of LeBit will be held by Joseba Ugaldi from the Maya Technology Center. He will give a talk about embedded functionalities in automotive interior. And the fourth, and not the very least, talk from an end user will be held by Rafael Michalczuk from Swarovski. He will give a presentation about innovation in functional decorative surfaces. Before I will go to the talks, I will also introduce you to our website. By sharing my screen. Can you see my screen now?
Not yet.
Not yet. Oh.
Yeah.
Now, perfect. Good. This is the LeBit website. You have probably been in here to register for the event. But if you would like to gain access to the LeBit service, the only thing you have to do is go here to the front page. Then you can register over here by this box, register and gain access to state-of-the-art services. Click here. And then there is this registration form you have to fill out. Your contact name, the company, your mail address, and a short description of your idea. Then there is 4 more steps. How mature your idea is, what you wish to accomplish with the help of the LeBit support, and how big your company is. And you are also able to upload a file here and simply submit. Then we'll come back to you. I know that Zachary Davis in his talk will also come into further detail what you can gain from this service. Another thing I also want to mention is we're gonna have these networking sessions. They'll be held in another platform than Zoom. They'll be held in the Wonder session. Don't worry, I'll put up a link in the chat so you don't have to look around now. When you enter this, you'll be asked which company you're from. Just type in your company name and access. Then you will see a table like this. You can zoom in and out here to see anything further. We have 5 areas where experts from this area will be able to answer your question and network with you. We have in nanomaterials, in formulations, in component, in line monitoring, and in techno and economical services. If you want to speak with a specific person, you can go over here and, for example, find a specific person in the participant here. Then the screen lights up and I can find Christian here, for example. Then I can go over to him or invite him to my circle. And a ring forms around and we can start to chat. You can, hi Christian, you can maximum be 15 people in a circle. So if you go over in one of these areas and the circle is already full, an expert will enter your circle and start a conversation with you. So don't worry about that. You don't have to be inside one of these 5 areas to have a conversation, but the expert in these specific 5 areas will be in these areas. If you go to the button on the screen, you can turn on your microphone and your camera. And if you go to the right side, you can change your audio input and your video input as well as your name. You can also chat with people in this networking. You can chat with the people in your circle. You can send a private message, or you can write to everyone. We have 3 networking sessions. One after the first talk, then another one after the 2 second talks, the third and the second and the third talk, and then one in the end. When the presentation will start again, I will go in and host in this Wonder Room, so you will not be locked out of Zoom, and you will know when we will start the presentation in due time. So don't you worry about that. If you have any question along the way, for example, after our presentation, please just go to the chat in the Zoom and write down your question. In the end, I'll ask the presenter the questions. And with any further ado, I think I'll give the word to Zachary.
All right, thank you, Nina. Very nice presentation and overview of the Wonder. It'll be exciting to see how that works. Now, we have been trying it quite a few. It works pretty well. Okay, I'm sharing my screen now, so everybody can see, hopefully, the presentation. So then I'm going to see if I can get rid of this. Yeah. All right, perfect. Yeah, my name is Zachary Davis. I am a team manager at the Danish Technological Institute, and I'm also coordinating the LEBED project. The LEBED is a Horizon 2020 project with the title Innovation Testbed for Development and Production of Nanomaterials for Lightweight Embedded Electronics. So first of all, then I just want to say just one word about why we are here. So what is lightweight embedded electronics? So the idea is that, you know, you probably, hopefully some of you or maybe all of you have seen a printed circuit board. It looks a little bit like this. Printed circuit boards, they come in all shapes and sizes, of course, but this is a sort of what we call a temperature logging component. It has an NFC capability, communication capability. You have a battery for energy. You have also some mounted components on the other side, a microcontroller as well. So this is what it looks like, you know, so using, I would say, the standard PCB technology that everybody knows quite well. This is, I says, it's a very mature technology. You can also make it in quite a large volume, so it's relatively straightforward. It's usually used making deposition and etching techniques, which could be, I would say, in some cases a little bit not very sustainable, but in all, it's a really nice technology. But what we want to do is then, how do we then embed things into appliances or products that can't, you know, that are not rigid, or maybe that you want a little bit less weight because you want to have more and more sensors, more and more electronics into, like, for example, buildings or cars and stuff like that. So what we want to do is sort of revolutionize the way that you make electronics from going to this sort of old school PCB to something that looks like this on the right hand side, where we then use printing processes and novel materials and to actually be able to print and mount the components onto flexible. It could be in this case it's some plastic foil, but in principle maybe even directly into textiles or into other and other substrates which are not sort of these standard PCB substrates. So this is what we're talking about. Why? And then I think this has a huge application base, and of course it also takes a lot of know-how. It's not just you make a design and you order it into. That's not the way it works right now. But that's what we would like to do, is to actually make a service, sort of, you know, what LEBED is sort of trying to aim for, is trying to make a service which you can come to a single point, and then you can get get involved with this type of technologies. So this is basically what LeapBed is all about. So this innovation testbed, or you can call it a hub, or you can call it whatever, is basically a collaboration of research and technology organizations and companies that can provide services, but also access to infrastructure within printed and embedded electronics. So it's all going through a single entry point, an SEP. So the idea is you have the SEP. Nita just showed it to you a few seconds ago. This website, you apply, and then through that you get you get into contact with the single entry point, which will then bring you through the different phases of LeapBed. And in this case, we have 3 phases. One is more of a techno-economic modeling or assessment phase, where we look at the idea, see how it looks. Does it make sense? Does it not make sense? There's a lot. I'll go into more details in a bit. You get access to infrastructure through pilot lines, and then we can also help you go to help you through the market once you have done a pilot project to show you how you can actually market it and go to the market with that. So there's quite a lot of services and a lot of expertise, and it's not just found one place. It's actually quite a few partners, as you see here. We actually have 13 service and pilot line providers spread across Europe. Quite a few countries actually, and you can see them here. I would say I also want to just to emphasize the pilot projects, or the types of pilot projects. We actually have many different types of pilot line technologies, nanomaterials, formulations, component printing lines, of course. We also have a lot of inline characterization and testing facilities in order to understand what we're doing, because it gives feedback to the different pilot lines, etc. So this is just it requires a lot of course organization, but this is what LeapBed has done. In order to sort of facilitate the LeapBed, the development of the services and the upgrading of the pilot lines that we have been performing in the last 2.5 years, we have 4 end user cases. We have Swarovski, we have Maya, Graphiatic, and Axion. I'm not going to say that much because they're going to come and tell you themselves what they are doing and what they're interested in, and how LeapBed has actually assisted them in their development process and their innovation process. Yeah. So just a little bit about the LeapBed journey. So this is you of course you go to the website and you push on the button. But what happens after that? Well, in principle, the LeapBed services is sort of you have most of the contact going through the single entry point, which is DTI, which is us, and also a project manager. And the project manager gets assigned to you shortly after you come into the single entry point. The project manager could be is actually represented right now by one of our major large I would say pilot line facilitators, and they're the ones that can actually can run a full a pilot project, and so they have the sort of the know-how, the expertise, the technical expertise to get things done. But okay, you sign up at the leapbed.eu, as Nina showed you. You actually you receive a URS form, which is basically a form that you need, a questionnaire that gives us a lot of information that we need to know in order to evaluate what we can do and how we can do it, and if it makes sense to do it. So this is I think it's over 4 or 5 pages of information that we need from you. So once you get the URS, you send that back to us. We make an offering, and we offer that to the customer. And then once the customer accepts that, then we start the phase 1. At the end of the phase 1, you get what we call a customer fact book, and this fact book has all the results, all the sort of phase 1 evaluations, which we'll talk about in a minute. And then, of course, this information goes into the pilot project, which is access to the pilot lines. The project manager group will then take you, and then all of these sort of, I would say, discussions and negotiations is going through, of course, the project manager partner. They will run it. They will run it together with you. They will then also subcontract other pilot lines that are needed. So usually a collaboration is not just one pilot line, but several different pilot lines, but it will all go through the project manager partner. Once you've done that and you want to go to the phase 3, this is sort of the SEP can also then takes over again, and then we'll assist you in trying to figure out which services make sense and making an offer for you based on the pilot phase 1 and phase 2. And then of course once you have accepted that, the phase 3 starts. So it's sort of in bites. We do a phase 1, which is more of an assessment part. What can we do? What needs to be done? Then of course the project happens, where it's actually obviously the meat of what the innovation and development, and then going to market. How do we transfer the knowledge back to the customer? That is in phase 3. Libet is of course very, very flexible. That means that once you go into the single entry point, I mean, there is of course opportunities that maybe you already have an idea and you already have actually a proof of concept. You just want to scale it up. Okay, then you can actually pretty quickly, if it's quite straightforward, maybe jump to a phase 2 or in an upscaling project. Or you already have it on upscaling and you need to access some business plan or some other types of services going directly to phase 3, then that's also possible. So there is quite a lot of flexibility on how and which, there's no set rules of, oh, you need to have phase 1 to 4 years. I mean, that's not the way it works. It's more this, it's a mix and match. So we need to make the services and access pliable to your organization and your needs, of course. The phase 1, just to go more details on these phase 1 services, we have 6 services. Technical assessment, which is a mandatory service, because we need to understand what the customer is wanting to do, what's the technology readiness level, what's the what is the sort of ambition of the customer, and of course then once that is finished, then there's also several other types of services we can do: safety, economic, LCA, pattern mapping, and if needed, pilot project financial support. Pilot project financial support, I'm not going to go into too much detail here, but basically this is a service for small companies or SMEs that don't have much capital, that because of course using the pilot lines that you're going to see, they're not they're not inexpensive, I would say. So if you need help getting support for that, we can of course help you with that. Just a short description of each of the sort of the services. The technical assessment is looking at the technical feasibility within Libet. Can the Libet expertise and pilot lines solve or do provide a solution for the client? We look at the risk level. What's the risk? Is it something that's way, does it require that we invent a whole new material system and then go from scratch, or can we just take things off the shelf and then mix and match what we have? And then so assessing the risk level. We also collect the data for the other services that are coming afterwards. And we also develop what we call sort of a preliminary system architecture and bill of materials. So actually already, and actually that's here, already after the technical assessment, we have a very good understanding of what is the client providing, what is the Libet expertise providing, what's going to come off the shelf, and what needs to be developed from scratch. This is done through what we call a system architecture and a preliminary bill of materials. Once we have done the technical assessment, we actually go back and then we can use that data to carry out the other types of services. We can do an economic assessment, because at the end of the day, I mean, if the product you envision, you probably have a cost target. So then can we meet those cost targets? How can we meet those cost targets? How much, and then we can actually both look at both the material properties and the cost, but also the production cost using different types of production possibilities. These are things we can do. We can look at the risk involved. We can also develop a preliminary business model canvas and etc. So this is some things we can do as well. Because of course, not just looking at the technical solution, which is important. Sometimes we also need to know or understand how much it's going to cost, and what will the cost of the product or the innovation be at the end of the day. Preliminary safety screening is also quite important. We need to understand if there are any risks because we're talking about, in many cases, printed materials which consist of nanomaterials. So we need to look at the regulatory aspects of those materials that are embedded into the product, the printed product. We have Techno, which is experts within this. They're really good at doing these technological and ecological testing, and we can also even go a step further and look at the components themselves, the electronic components. I mean, there's also a lot of standards in the mechanical and the environmental properties of these things as well, so we can also take a look at that. Life cycle assessment is looking at the sustainability of the materials, but also the processes involved. So going from a PCB process to, for example, a print process, how and also the materials involved in there, how will we improve the sustainability of the product? We can look at that and look at contributions to climate change and resource uses, and have both, and also look at not just during the manufacturing, but also the whole life cycle of it, so the recyclability, etc. Last but not least is the pattern mapping. In this case, we're looking at the IPR sort of landscape of the ideas. So maybe it's very important for the client to understand, okay, I have this really cool idea. Is anybody else doing this? Who is doing it? And what the pattern mapping service can do is tell you exactly all the information you need about that. Who's doing it? Who's patenting around this ideas? What locations are there? So try to figure out who your competitors are, and if there's a freedom to operate here. So now I'll talk a little bit about the services. Now I want to just give a very, I would say, quick review of the pilot lines. I cannot tell you everything because there's so much stuff to tell about, because there's so many partners involved and so many really exciting innovations coming out of the work we're doing at Liebed. At the end of the presentation, I actually have a list of some links. If you want to have more information, please go to the links. We have actually some webinars we did in the fall, and also some PDF documents, etc. And of course, these things are being, and then there's also an updated list on our website. So, and this is being updated continuously. So if you want to get the newest innovations, then you can take a look there. But if we start with the nanomaterials, so in this case, nanomaterials, we are looking at both the sort of, and this is mainly work at DTI, looking at both the sort of screening of new materials, but also how to upscale and produce large amounts of these materials. And that's actually been quite a big, I would say, bottleneck within industry, that you have, of course, I mean, the materials that are used in printed electronics is mainly these silver microflakes or silver-based products. These are quite mature, but if we want to implement new materials that have new functionalities, or more sustainable materials, or even stretchable or whatever, then this takes a lot of time in both the research and development part, but also the scale up. And this is what we're doing. We have both the batch and flow reaction technologies. We build reactors based on I would say small scale. Once we have a sort of a material that we have then studied, then we can actually build a reactor around that. We can use batch reactor technology, flow reactor technology. Most of the reactors we have are PLC automated, using inline process monitoring. Another thing we're looking at is just not just the actual production of it, but also the filtration, because that's actually a huge barrier. So once you have produced, let's say 100 kilos or 100 liters of nanomaterial suspension and liquid, but you also have it together with a lot of byproducts, and you need to clean that. So cleaning, 10 liters is actually, I would say you can do with a centrifuge, but actually cleaning hundreds and hundreds of liters in a production facility, this is actually it's quite tedious and time consuming. So what we've actually done is taken what we call cross flow filtration, sort of a bench lab scale a unit doing this type of thing, and then upscaled it to a production level tool. And this is something we just finished, actually. I took this image yesterday, and we're just testing it now. And we plan to sort of validate the process within the next couple of weeks. Some of the materials that we've been working with, copper, silver nanoparticles, silver nanowires. Actually, I didn't have a picture, but we just had actually quite a breakthrough using, being able to also produce copper nanowires now. So this is actually quite exciting news for us. And we're trying to sort of, we're at the very beginning of this, but still we're trying to review this discovery. We're looking into sort of hybrid materials, so carbon with metallic embedded particles, dielectric materials, ferrite and magnetic materials, oxides, ceramics, etc. We can do quite a large variety of materials. We also have another pilot line, which is made through our partner VS Particles, looking at gas phase nanomaterial pilot line. So basically, it's using a arc ablation process, which is then being able to take a bulk material or more than one bulk material, using arc ablation to actually sort of aerosol or make small nanoparticles, and then a flow system, airflow system, in order to carry the particles and then deposit them and draw them basically onto a surface. So in this case, what you get is a local deposition of your particles onto a substrate in any sort of pattern you see fit. This is very interesting and very nice, and I know I can't go into all the details, and well, these are used for I would say sensor applications, gas sensing, maybe CO2 or CO gas sensing, and other types of interesting applications. This is also just showing you how it works. It actually they have the pilot line is actually up and running. So if you really like to go in and take a look at that, please contact them and get some more information about that. If we go on to the sort of the next type of nano-enabled formulation pilot lines we have done, of course, a lot of different things. I'm just going to give you a few highlights. And one of the things that I think is pretty interesting is the sort of, and also, again, we identified this as one of the lead-based innovations is trying to bring down development time to reduce that. And one of the things we've been doing here, and this is work done by CPI in the UK, is combining AI and robotics in order to really sort of optimize the development phase of making a conductive or a nanoparticle type ink. So what they're doing here is they take some of the particles, in this case it's copper particles from our from one of the nanomaterial pilot lines, and actually conducting an experiment where we're trying to find which solvent is and which materials are compatible with the particles. So in this case, we did design of experiments and used the robotic capabilities of CPI to both mix and also test many different ink iterations, the ink formulations, and then be able to compile a sort of a list of which particles and which are compatible with which solvents. And this, of course, helps us really go quicker to inks that are more stable, that work, and actually can be then developed into real inks that are used in the pilot lines. This is just to say that we have continued that work, and so we took the copper, we actually, based on that work, developed a few different types of inks, and one of them an inkjettable ink, which is then, of course, used by us and other partners in order to make some of the components. And where copper in this case is a sort of a more cheap and I would say much more sustainable product material than silver. We also have Rise working on zinc, and zinc is an extremely nice material because it's also quite cheap and quite sustainable compared to the silver. And also they are been able to achieve a nice, I would say, stable, conductive, and inkjettable ink. And they're also using it in their own pilot lines, their own printing lines, you'll see in a minute. So this is a very nice alternative to some of the other materials we've been developing as well. But then we have Athena working on different types of color-based inks. So in this case, they this could be interesting for packaging. So if you want to use color for, I guess you can use it for gas, specific gases or temperature, humidity, pH, this type of thing. Then you can use these sort of color-based inks in order to actually give you a visual indication of what you're doing. And this is very nice for packaging. On top of inks, we also do other things. Formulations is quite a broad term, so we're also looking into adhesives, because when you're working with flexible foils, plastic foils, you cannot use standard soldering technologies. So soldering onto a plastic foil will just melt it. So in this case, we use conductive adhesives, so glues. And this is something that CPI is also looking into. And so in order to really attach dyes, then we can actually use both to develop anisotropic and isotropic adhesives that can be used for mounting different dies. And this is actually also ties together with some of the production pilot lines they have as well. We'll see in a bit. We also look into nano-enabled resins. So actually, being able to make composites that have, I would say, tailored functionalities based on introducing nanomaterial. And this could be for EMC shielding. This could also be for other types of antibacterial effects, et cetera, et cetera. There's a lot of different things. So also thermal conductivity, this type of thing. So introducing these type of things is also something we're working on as well. The last type of pilot line is these component pilot lines. In this case, we have quite a few tools and to play around with. We try to sort of, we have quite a few partners that have quite a few different types of equipment. And we try to sort of, characterize into two different categories. One is sort of a prototyping, sort of a small to medium scale production, and then we have, of course, the more production upscaling technologies where we are talking about roll to roll or large sheet to sheet type of equipment. So just some examples of that. We have both the DTI and RISE have inkjet printing technologies, capabilities on the sheet to sheet level, which is very nice for testing of new inks, for prototyping, for doing small scale studies, working with different materials. And this is just some of the things that we can do, or some of the equipments we have. This is just some examples of things you can do with this type of technologies. You can print coils, touch sensors, humidity sensors, strain gauges, thermocouples, you name it, we can try to do it. You can work with different technologies, different materials, and I would say this is a very nice for you. You make a design, you start to print, and maybe you have something within a few days, and then you can start to test it, and then you can make this in a very fast iterative process to actually optimize design, look at different materials, etc. Another really exciting innovation in Libet is this 3D multi-material. This is done by TNO and Holst. So this is a sort of combining conventional 3D printing with also some conductive materials, etc. So this is an example of where they actually use SLA printing to print cavities, and then they filled the cavities with components. Then they printed grooves, and then they filled up the grooves with some conductive, in this case, silver paste. And then they encapsulated it with the 3D printing technology. So yeah, in this case, it's a fully embedded passive temperature logging system, fully 3D printed. And this, of course, once this is getting, this is getting more and more mature. So in this case, you can really think about truly 3D electronics using this type of technology. We also have these sort of more, I would say, large scale or large area type of printing systems. These are some examples of sheet-to-sheet screen printing. This is where we have both the TIN and RISE having this type of equipment. We also have, RISE is also developing a large area roll-to-roll inkjet printing system. So basically what they're doing is converting an old poster printer or sort of poster printer to a printed electronics printing system. Extremely exciting. So you can really make big areas of printed electronics on a poster format. This is really cool. We also have roll-to-roll technologies, flexographic, inkjet. I think also is rotary screen print. And in some cases, it's not written here, but we have that within the consortium. So we can really go up to sort of industrial production volumes if when we want to do that. Pick and place systems, of course, we have sheet-to-sheet pick and place systems. If you want to, mount temperature or capacitors or resistors or microcontrollers, this type of thing, this is what we need. And last but not least, we also have, I would say, the big brother to that is a roll-to-roll assembly system. This is a system that CPI developed, has developed and has been developing the last many years. And this is a really, really interesting line, which is basically, so then you can take your roll-to-roll print, put it onto the roll SMT assembly system, and then do your mounting on a roll-to-roll frame and not on a normal sheet-to-sheet, which you do it today. Extremely exciting technologies. The last thing I wanted to show you is also the embedding part. So actually putting, making components, printing them, but also then embedding them in different sort of, using resin infusion systems is also something we're looking at. So if you want to do this, I think this will be more evident in some of the applications we've been doing. So I'm not going to take too much of that. Just as some examples that have been fabricated by CPI. I also want to mention a little bit some of the online and inline monitoring systems we've been working with. So SIA List has been working on a XRF system that can then, as an endpoint detection for our nanomaterial pilot line. So actually, this system can then monitor the difference between a copper salt, a copper ion, a copper oxide, and a copper pure copper particles. So we can actually use it to sort of, monitor the product as it's being done, and then we know when we're finished making our particles. They're also looking into using X-ray imaging in order to sort of, as a sort of candidate, sort of not as in order to look at printed components to actually see if there's scratches that will then, of course, because you get a much better contrast using X-ray imaging compared to, for example, optical imaging, as you can see on the right-hand side here. Very exciting. We also have roll-to-roll automated test lines. This is both CPI, I think also TED is looking into this. So once you have made your products, you need to, and if you have tens of thousands of them, then you need to test them. Then we can also have automated, test lines to do that. So then you can also, both program or test or whatever using these type of technologies. Finally, last but not least, is the micro, I would say, non-destructive testing of some of the circuits. So sometimes you don't know, there is a failure, you're not exactly sure what happened. Then we can use things like micro CT scanning, electron microscopy, and other metrology methods in order to really, cut the, to look into electronics and try to see what has happened. This is an example of that. So this is giving you more of the, all of the capabilities. And of course, the last sort of phase is the knowledge transfer. In this case, I'm not going to go too much details. This is actually, these are services that are being formed and developed as we speak within Libed. So more information will come in the next, I would say, half a year. But these are things that are talking about IPR and patenting strategies, standardization, safety, business planning, investor capital access, etc. And with that, I want to sort of, this is basically a very, very short overview of what Libed does. If you want more information, please go here to our webinars, both the PDF versions and webinar versions on our YouTube. Please do that. And the last thing I want to show you is the open call. This is basically what we are doing now. So what we want to do is we have now, I would say, matured the services to a point where we want to open them up to and then give the chance for external industry to come and use our services. So we have this is what we're doing today. We're sort of announcing our open call. That means that and then we'll have a cutoff date around the 1st of September. So you can go to Libed, sign up, you get a URS sheet, you fill it out, you send it back. And then around we're going to collect those until the 1st of September, and then we're going to make a decision, and we're going to award 10 companies with a free phase 1 service package. We'll do a review process. That'll probably take a few months to do that, and then we'll start to notify the companies whether or not they can receive a free service package. And then, of course, around October and onwards, we'll start to do the phase 1, and it usually takes a few months, and then you'll get a fact book. And then, of course, from the fact book, you'll be able to gain access to a phase 2 or phase 3, a pilot project, and then we'll help you how to get involved with that as well. So that's very exciting. So I really encourage companies that really would like to, are interested in this type of technologies and what we can do, to go and sign up. We'll be in contact with you very, very shortly, within a few days, and then we'll start the process. And with that, I want to say I don't have that many more words for myself. I'm not sure we have any time for questions. Maybe a few. Otherwise, I say thank you for your attention, and I hope to see you in the either questions now or in the in the Wonder. All right.
Thank you, Zachary. And yeah, if you have some question, please just type them in the chat box.
Yeah.
I'll give you a few
There's some chats
seconds.
already.
We haven't received any so far. Okay, else Zachary will also be, you'll be able to have a chat with him in the Wonder session. So I'll just give you the link for the Wonder session. Oh, hang on 1 second. Like this. So it should be in the chat now. So you'll be
I can
able
see
to.
there's one. There was a question.
Oh, I'm so sorry.
No, it just came right when you were when you chatted.
Yeah, we have. Can you corroborate with DTU concerning IPR and nano development?
Of course. I mean, yeah. I mean, that's no problem. I mean, usually we have some standard, I would say, IPR working with companies, and of course, IPR generation of IPR is always some. I mean, the general. We have some general rules about IPR and how we usually work, sort of standard operating procedures on this. But of course, we're always willing to discuss and negotiate these type of things. So that's not a problem at all.
Yes.
There's one more message.
No, that was a.
Okay, that was just that. Okay.
Error correction. So if you want, just please jump into Wonder, and I will let you know when you have to jump back to Zoom, and I'll also send you a link in the chat in Wonder. If you have any issue, I'll be jumping back and forward both with Zoom and in Wonder, and you can just find me. My name is Nina Ritter Nielsen. So I will definitely encourage you all to go to the Wonder session now.
Can you see the screen?
Yes, we can.
Perfect. Hi, I'm Alejandro from Graphieti, and I'm going to speak about our user cases in the Libid project. The points to follow are: first, who we are; second, our objective in Libid; the three, phase one, assessment; phase two, pilot project; phase three, knowledge transfer; and six, conclusions. Okay, first, who we are. Graphieti is a label factory founded in 1994. It belongs to the Lara Group, which is made up of 8 businesses around Spain. We are actually manufacturers of labels and also official distributors of Toshiba and Epson barcode printer, as well as their respective consumables like inks, ribbons, spare parts, etc. All this supported by our technical service. In relation to the previous point, we can provide the client with all the auxiliary elements that they may need when are working with our labels, such as rewinders, unwinders, electrical and manual labels applicators. I would like to comment that the Toshiba company, with which we have been working for more than 25 years ago, this year, 2021, we have been awarded as Premier Business Partner, which translates into being the most efficient brand distributors and therefore leaders in sales of bar pre-coder. This year, we sold more than 1,000 printers in this year. Our main products are labels, anonymous labels, and printing labels, with a wide variety of qualities and size and formats. We produce ITU labels. It's like the Ministry of Transport Taste in UK to different regions of Spain for more than 10 years. We also produce barcode labels for more than 80 hospitals in Spain. We have a reprint department made up of 6 people. We also sell hospitals bracelets. And the health cards of the Valencian community, we manufacture them since 1996. And we are also in the RFID tags and system roles. Some of our clients are for and consume. In these pictures, you can see a typical printed hospital label. There are our markets like feeding, industrial, chemical and chemic, commerce, pharmacy, luxury goods, hospitals, and automotive. And the needs that we have detected are authentication, traceability, control of ambient parameters. For this printed electronics can offer new products, reach new markets when we are not present now, and differentiation from the competency. For all this, we want to explore this new technology, and for this our objective in Libet is this. Now I'm going to speak about case 1, ambient conditions monitoring. According to the needs and the demand of our main markets, we present to Libet 2 different cases. The first case, the objective was the monitoring of ambient conditions. To be precise, the objective was to control the environmental conditions that ribbon printers are exposed to when printing. The application will be applied in ribbon printers. And what's the problem? Toshiba printers works well between normal temperature and humidity ranges. If the printer is in extremely hot or humid conditions, it may cause failure of the CPU and the printhead. The warranty doesn't cover these damages if the printer has been exposed to these factors. Some customers who do these bad actions complain about the printers and ask for the guarantee, but they are not telling us the truth about the working conditions of the printers. Solutions. We have thought that the solution to avoid this is the creation of a label that is capable of measuring the temperature and humidity of the environment during the printing process. And what are the benefits? With this label, we can have the printer monitored at all times, and it will no longer be possible to make inappropriate use of the guarantee and avoid economics and material losses. Requirements. These were the requirements that we wanted the printer labels to have in order to control printing conditions. Temperature threshold, 5 and 35 degrees. The optimum temperature, which guarantees the correct functioning of the printer. When the temperature threshold is exceeded, the label will record the date, day and hour. Humidity threshold, 20 and 80%. Continuous reading. The data will be read every 30 minutes, and the information will be downloadable, and the communication will be with NFC. The label will be placed on the goods, so the dimension should be different depending on the printer. And the cell life is more or less 2 years. Now I'm going to speak about case 2, authentication. The second user case that we were interested, it was focused on authentication. One of our products is thermal transfer printers. In those printers, the heating elements of the printhead apply punctual heat to the patient ribbon. Ribbon is a transparent polyester film in which a mix of wax and resin is placed on one of its faces. When it comes into contact with the printhead, it heats up and melts the mixture, depositing on the adhesive label. We sell hundreds of thousands every year. The ribbon and label stocks must be carefully matched to each other and to a specific application in order to receive optimum quality and durability. We usually offer a guarantee of 1 year for this kind of printers. What is the problem? Some of our clients don't use the ribbon of our printer. They use ribbon for other trademarks. In those cases, the durability of the printer can be drastically reduced. At this moment, we cannot identify if our customer has used our ribbon or other, and this fact causes us economical losses. We want a solution that allows us to detect that other ribbon has been used, and in that case, we could demonstrate it and cancel the guarantee. The scope of the project is to develop solutions that allow us to demonstrate that our printer has not been used with original ribbons. If we reduce our economic losses due to printed files when not original ribbons are used, we will be able to extend our guarantee from 1 year to 2 years. It will be longer than the guarantee from other providers. The original ribbon is more expensive, but it guarantees that there are no voltage peaks that affect the CPU and the printhead. They are the most expensive elements of the printer. Sorry. Solutions: an anti-counterfeiting label for ribbons. The label will notice if the ribbon is original or not. And benefits: we avoid that the client uses poor quality ribbon, which breaks the components of the printers. At the same time, we keep the guarantee of the ribbon intact. And now, requirements. These were the requirements that we wanted the printer labels to have in order to control printing conditions. The label or tag should be placed inside the ribbon roll. We want that users do not realize that the ribbon has a label, tag, or similar that alert us that they are not using original ribbon. If it's placed at the end of the roll, it will be impossible to locate. Our printers have the option to work with RFID. It could be a good type of communication with the ribbon. Now, phase 1, assessments. We presented our cases to Libet. For that, we complete a user requirement sheets. The information was analyzed and a project leader was assigned. In our case, Itene is the technical responsible of the development of our prototypes. The technical viability was studied by Itene, based on the information from the URIs. The technical challenges are valid. At Libet, developed printing process to produce conducting tracks will be used and commercially available components for the sensor application and controller will be integrated. While from the technological perspective, the idea is fully valid. The financial surprise is determined as a significant risk at this point. So, in order to reduce it, we contemplate the possibility that the labels could be powered by the printer itself. But we want to validate this idea with Toshiba when we have the printer prototypes. Now, preliminary safety screening service. Other of the services that was done previously to the pilot has been a preliminary safety screening service for Libet partners to easily find possible regulatory aspects about nanomaterials in any of the steps of the life cycle of the product. This platform also allows to find psychochemical and toxicological properties of nanomaterials and offer a fast communication way to ask for different nanosafety services. In that case, we will be customers of products containing nanoparticles. It then analyze our case and propose us a list of assays that will be further developed in the phase 3. Economic assessment service. Also, a preliminary economic assessment was done by Sustainable Innovations for providing a first estimation on the cost and revenues structure, return on investment, and a preliminary business canvas. Bearing in mind the expected selling price and volumes, the currently available cost of components, and the data provided in the URIs and user cases. The preliminary evaluation detected that our initial target price may be too low. Therefore, it will be necessary to check in fast through the cost of all manufacturing components for the final design to safely demonstrate the economic feasibility. And the conclusions are high risks, Continuous monitoring will increase the product final price, and power shall be provided by the printer. Now, environment point of view, due to the significantly different scales of the materials, additionally, as some of the components were not defined, the assessment was performed at a very initial state, and it will be reviewed in phase 3. And finally, the pattern mapping service was not done due to the uncertainty of economic feasibility in the scope of LIBE. And what have we learned from this phase 1? The solution is more expensive than our initial objective. There are options for printing NFC and RFID antennas using the facilities of our group, but they need to be studied. List of nano safety tests needed to guarantee the safety of our product. Overview of the new business model and cost analysis. Overview of the environmental impact from production to end of life of my product and how it can be reduced. And now I'm going to speak about phase 2, pilot project. The next step was the pilot project development. We belong to a group of companies and we have the capability to print labels by different systems. Those systems are flexography, inkjet, and screen printing. Regarding to printing electronics, each system has advantages and disadvantages. For example, flexography advantages is fast and commonly used in a label production, and disadvantages like required conductivity is hard to achieve due to the low ink thickness of the systems. Additionally, to different printing systems, we have different drying systems. For flexography, inkjet, and screen printing, we commonly use UV curing, but in screen printing, we can also use temperature drying. Regarding the adoption of the printed electronic industry, UV curing is higher risk, and the offer of inks is very reduced. Thermal curing inks are more common, but this system is not commonly used in the label industry. And finally, the filling conductive material can be copper or silver, although other particles can be used. These particles offer the conductivity needed for the development of antennas. The advantages and disadvantages of each compound are summarized in the table. And now, at this point, for the development of your cases, the partners are the Danish Technological Institute is responsible to creating the copper nanoparticles that will deliver them to CPI. And CPI will develop a UV curing ink to print by flexography, and Itene will print it, with the aim of having a low-cost solution printed by flexography, in addition to using this ink developed by the consortium. It will also evaluate existing commercial solutions to give us alternatives. Now, screen printing trials. Test has been done in both screen printing and flexography printing to see what printing results we have. In screen printing, we have used 3 types of inks: a commercial non-conductive ink, a conductive ink thermal curing, and a conductive UV curing. This is the one that interests us. The objective is thickness. The objective in thickness is 1000, so the line thickness is higher than was expected, because we wanted 100. So that can mean lines are too close and possible crossings could be done, and this is bad. The resistance, the thermal curing is 42. That is the objective. When we use the UV curing, the resistance is 114, but with 2 paces is 77. It's too high for us. Analyzing the viscosity is quite different. The UV curing is higher and has a thixotropic behavior. And now we have made an analysis of the substrates that we have to see what temperatures they resist, because for the curing of these inks, it is necessary to expose them to high temperatures. In this picture appears the different substrates that we have and its resistance to the different temperatures. We can see that the PP white gloss is the one that holds the temperature worst. Eos in general withstand temperature well, but turn yellow at the end. At the end, we have printed the antennas on the paper white mat. And now the flexography printing trials. In flexography, we have done the same steps as for screen printing: a commercial non-conductive ink, a conductive ink, thermal curing, and a conductive UV curing. The thickness is non-conductive, and UV curing is quite similar, but the resistance is better in thermal curing. At the end, the print quality has not been very good and is necessary to continue working on it. And now, what will we get out of this phase 2? A price list of materials, the conditions in which these prototypes should be manufactured, and incorporation of new equipment that we will have to deal with. This information is important for phase 3, 2, business plan services and investment capital services. Prototypes to validate the idea with our printer provider, and important marketing tools for our providers or clients. And now, phase 3, knowledge transfer. Ongoing APR and patent services, standardization and safety services, business plan, and investments capital services. These last two are ones that interest us the most. What will we get out of this phase 3? Economic assessments, detailed financial assessments like projection on cash needs and financial performance, overview of the attractiveness of the project, setting financial management objective, and detecting potential financing sources, and investment capital services, financial advice, optimization of the business plan, develop of financial model, etc. So these two assessments are the most important for us to evaluate the viability. We have to APR and patent support in case our product could be protected by a patent, and needed nanosafety analysis. And at the end, conclusions. Participating in the LEAD project helps us to explore new possibilities, open new markets, evaluate the pros and cons for our company, investment and modification that could be needed, and marketing tool for us. Thank you so much.
Thank you very much, Alessandro, and thank you for a nice presentation. If any of you have any questions, please just post them in the chat and we'll take it from there. I'll give you a few seconds. Yeah, while we're waiting for the question, there's one. What are the criteria or requirements? Oh, I'm not sure this one is for Alex. This one is, I think, for Zachary. What are the criteria and requirements for the open call?
Okay. The requirements, can you hear me?
Yes.
Okay, good. Yeah, criteria that you're I mean, in principle, you have to be a European state member. and you have to have have some sort of I would say be in a company or an SMB or even a large industry. These there in this case is not too much, or even another stakeholder. That doesn't mean, but you have to definitely be in a part of the EU or a European country in this case. That's mainly the only real criteria. Otherwise, you have to do a very interesting case. These are the way we sort of judge it will probably be based on, of course, how interesting and how well does the case fit to what we are doing, these type of issues.
Yes, I guess that was it. I haven't received any questions. Please just interrupt me if you have a question. Mm-hmm. If not, I think we'll go to the second end user case with Araceli Galvez Moreno from Acciona, who will give a talk about embedded IoT components for the construction sector.
Hello. I'm going to share my presentation.
Yes, please do.
Yes, that's okay.
We don't see it in presentation mode.
I'm sorry. But no, yeah.
Perfect.
Okay. Hello, I'm Araceli Galvez. I'm a researcher, as Nina said, in a new materials group of technological center in Acciona Construction. Acciona participates in Libate project as one of the end users in the incorporation of the developed technologies in the construction sector. First of all, I'm going to briefly present you Acciona. Acciona is a global company operating in 4 main business lines: infrastructure, water, energy, and services, with an objective to provide solutions to all these sectors in a sustainable way. Currently, in Acciona, we are more than 55,000 of employees, and we have office and projects in more than 40 countries. And in the back, you can see all our presence worldwide. Acciona has 3 technological centers, one in Madrid for construction, one in Barcelona for water, and one in Pamplona for energy. I want to focus on Madrid Technological Center, as which participates in the BET project. Here we are an international and multidisciplinary team of around 70 researchers involved in more than 50 projects at national, European, and international level. The center has 17 research labs and a production workshop for the production of large-scale prototyping. The objective of the center is the development of new technologies, materials, services, and processes with direct application in your business, providing a competitive advantage over other construction companies. Acciona has been working with polymers and composite materials for the last 15 years to build unique civil infrastructure structures. The benefits of use fire-reinforcing polymer are numerous, but the mechanical strength, the chemical resistance, and lightweight make composite ideal for some important applications. Our work has also been recognized at international level. For example, in this picture, we can see a footbridge in Madrid, in one of the most touristic areas of the city, a waterproofing system in a high-speed tunnel for the train of high speed in the north of Spain, and our famous lighthouse in Valencia port, This is one of the most significant structures to show the high durability of these materials in hazardous environments. And now I'm going to explain why we are working in Libet and how currently we manufacture composite materials, and how Libet will help us overcoming those challenges to produce it. In the manufacturing and installation of composite elements, we use different type of sensors. First, during the manufacturing and post-manufacturing processes, we use temperature sensor to monitor and control the process parameters. These sensors are long wires that we had to put along all the workshops, and not connected to an equipment. In this picture, we can see two processes where the temperature are monitoring in pultrusion and in vacuum infusion processes. And another step that we use sensor is during the transportation and installation. We use tracking speakers to store information of every piece and keep the traceability of the component. With a BD code printed in the sticker, the part is identified and traced. And the third step when we use sensors is during the operation stage of the structure. It's important to analyze the structural health of the infrastructure. With the monitoring of some physical parameters, it is able to increase the durability, to predict failures, and to program maintenance. This picture shows one of our pedestrian bridge with externally installed wire sensor that we use to analyze the strength of the structure while it's in use. There are a lot of wires and equipment we had to put, and we had to install close the bridge. In this other picture, we can see our lighthouse with sensor too, with wiring sensor, with connection. At the end of the process, this is a mess of wires. The use of wire sensor during the production have some challenges for us. Difficult to handle because it used to be long wires with delicate connection. Cause the lamination, the piece with the embedded sensor must be discarded, and the data reliability is not 100%. The same occurs with the sensor for traceability. The adhesive can fail and the long wires can break. In Libet project, the design and production of wireless sensor will substitute the wire sensor and all its drawbacks. The solution proposed is the use of embedded printed sensor with NFC or RFID technology. This sensor must receive the chemistry of the resins, the temperature of the process, and pressure or vacuum. And the sensor should get confident measures that allow in function and few meters of measurement range. Specifically, the wireless sensor produced in the project for Acciona case are temperature sensor and asset tracking sensors. The process is uses for the incorporation of sensors in components need high temperature and pressures, and batteries can survive this condition. So an energy harvesting design was developed. The temperature sensors are designed to operate up to 120 degrees to survive the resin cooling temperatures, and the asset tracking sensors are designed to survive up to 180 degrees and are redesigned to improve the resistance to pressure because they are going to be embedded by pultrusion technology. The sensors are designed according to European codes and consist of an integrated circuit electrically connected to the antenna. The antenna is printed with conduction material developed in the project. Our partner CPI is in charge of this part in Acciona case. The production of a sensor. The production of a sensor has 4 steps. First, to specify the electronic circuit design, print a screen as plate, and identify the materials required. Second, to print the antenna onto the substrate after the formulation of conductive inks and adhesives. Third, to integrate the electronic components onto the device. And the final, to test the performance of the final device. In the assembly of the sensor, the conductive ink and the conductive adhesive must be selected to meet the requirements on the bedding process. What I said before, the high temperature, high pressure, and special chemistry. And have to meet the requirement for the electrical conditions too. The read range, the resonance frequency, and its function. The results obtained at the moment are according composite production with vacuum fusion lamination, not with pultrusion. Only the temperature sensor has been used with 2 technologies, MFC and RFID. The sensor have resist chemistry, the high cooling temperature, and the vacuum, 150 millibars. The first tests were made with sensor with MFC technology. During all the steps of the production, or the lamination, or the composite production, the sensors were working. And after 18 months from the lamination, last month, the sensor keep working. After that, RFID sensors were produced to fit better in our requirements. They are embedded in lamination with 2 typologies of resins and 2 reinforcement fiber, glass fiber and carbon fiber. And as we expected, the sensors don't work with carbon fiber because it's electrically conductive. In the lamination with glass fiber, the operation of the sensor is tested when the sensor is on the surface and it's between glass fiber layers. All the sensor works. The next step in the project are the evaluation of how the embedded sensor affects the composite, and if the sensor resists the corrosive environment and the vibration of the structures where composites are located, in the bridge, tunnels, and lighthouse. As conclusion, the development of reliable sensors to be incorporated into infrastructures to monitor the behavior of the composite will allow Acciona to guarantee the safety and correct functioning of the structures with the optimization of global costs. That's all. Thank you very much.
Thank you very much for the presentation. And if you have any questions, please put them in the chat. I'll just wait a few seconds before we move on. We have one question here. Do you think that the outcome from the project will be implemented at Acciona? Araceli? Azeli, can you hear me? There was one question. Do you think the outcome from this project will be implemented in Acciona? It seemed like the connection to Azeli dropped out somehow.
I hear you, Nina, so maybe it's yeah.
Okay, good to know that at least it works from this end. Araceli?
Yes.
Oh, you can hear me? Good. We got one question. Do you think the outcome from this project will be implemented into Acciona?
Well, I think that is the idea because do you know that at the first moment our idea for the sensor was more regarding the strain to evaluate the strain of the structures, but with some impediment we can do it. But the asset tracking and the temperature it will be important parameters to measure in real structures. So we can achieve the sensor that support the condition of the composite production. I think it can be implemented. Yes.
Okay, super. And there's one more question. One asked to the cost target and volume expectations. So what will be the cost targets for you and what will be the volume expectations? Araceli?
Yes. The cost
Target and volume expectations.
and the volume expectation. I don't know. That's
Hello, I'm Eva from Acciona. Also, I can help a little bit. About the cost, we really don't know because maybe David Johnson can help us because we don't know the cost of the final cost of this new sensors developed in the project in comparison with the sensor we are using now, our thermal couple sensor. In terms of volume, we use this kind of sensors to control our production, and we use every day or every week in infusion and in pultrusion to monitor the production of our profiles and of our pieces. The volume maybe I don't know. 10 sensors per week, and that is in 1 year, but you can imagine it's a lot because we put some sensors in different parts of the piece we are producing. And for example, to control the pultrusion parameters, we monitorize at least once in each shift or in each turn, at least 3 times in 24 hours. So the consumption will be higher, but really, to be honest, at this point we don't know the price of this new wild development. I don't know if something from CPI can help us.
I can comment on that. Can you hear me okay?
Yes, we can, David.
Great. Okay, so there is a cost target written into this use case, but which I don't think is something that I can disclose as far as I know. So there is a cost target, but the actual final cost of these sensors, it will form part of the techno-economic assessment. The asset tracking sensors being made out of materials that are already commoditized. The temperature sensor is using a chip that's in development and therefore has a higher current unit price because it's a development product. So part of the project's going to have to be figuring out, well, what will actually be the volume price of that that device. So it is slightly complicated by the fact that when you're developing something new, the unit price at the development stage isn't the same as the unit price at production. It's a pretty obvious statement, but yeah, those are being considered as part of the economic assessment, which is part of the LEBED offering.
Yes, I think that was the end of all the questions we have now. I will again post the link for the Wonder session, and we'll already start the Wonder session now. The talks will again start at 3:30 Central European Summertime. So in 45 minutes, we'll hear the third talk from one of our end users, which is from Joseba Ugalde from Maya Technology Center about embedded functionalities in automotive interior. We're a bit ahead of time already. So you'll have quite a long time in Wonder already, but we will start the next talk at 3:30. But please all go for the Wonder session and have a chat there. If you have any issue, I'll stay here online and you can ask me any question you like. Yes? Hi everyone and welcome back. Now we'll start with the third user case, and this one will be represented by Joseba Ugalde. He's from Maya, and he will give a presentation about embedded functionality in automotive interior. Joseba?
Okay, thanks, Nina. Okay, we'll present then our Myers user case that is, as Nina mentioned, embedded functionalities in automotive interior. My name is Jose Ugalde. I'm project leader in research and development department in the Meyer group. And let me introduce my company just a little bit. Meyer is one of the European leaders in decoration of plastic parts and also a manufacturer of complex injection molding for the automotive industry. I have to say that we are 100% focused on automotive industry, and we are a company that was founded in 1975. As I said, we are well known for our decoration, but we also integrate functionalities in our parts. For example, lighting and electronics, but using standard components or standard electronics, they say. I have to say that Meyer is a truly global player due to the last joint ventures that we've got, and well, we will see it in the next slide. And we have 4 technological centers. The main one is in Spain, in the north of Spain, and we've got other in China, India, and USA. Just a quick view about the global footprint. We are focused in Europe mainly, with our headquarters in the north of Spain near Bilbao, and different manufacturing plants in Spain, but also in the UK, Czech Republic, and Italy. As I said, we have a global footprint due to the joint venture that we've got with an Indian company, where we will go to manufacturing plants, and also in China with also 2 manufacturing plants. The last one that was opened is the one that was in Mexico, in San Luis de Potosí, that makes us just to be able to deliver all around the world, let's say, and to be able to go with global projects for the OEMs. In terms of main figures, our sales are going around 300 million euros, and we have a workforce of employees of more than 2,500 people. And what are the type of parts or what we produce? Well, our main portfolio could be this one that we can split into different businesses, all of them in automotive, exterior parts and interior parts. For exterior parts, I have to say that we are normally tier 1. That means that we develop and deliver and produce directly to our OEMs, to the OEMs. And our main parts are starting from the front module, front grills, fog lamps, and Fogland trims, down lower grills and so on, going with side pillars at the part that are in between the windows, decorated parts, wheel trims, also full fuel modules or charge ports for the electric vehicles, and also for the rear modules, some garnishes just to emblems or trims to open the door, the back door. If we go to interior, we are in this case normally tier 2. That means that we produce and develop for one tier 1. That is, for example, the one that makes all the door panel or the door. And we produce, for example, in this case, some aesthetic trims with some functionality options for this door panel. The same for IP components or central console or fascia environment. Okay, if we go ahead to the challenge that we want to solve in this LIBET project, let's say that our main objective or my goal is to obtain functionalities by overmolding flexible electronics in order to obtain a fully functional component that can be assembled without any process more than let's say one part. No? Instead of having different kind of parts assembled all together to achieve the functionality. So the desired functionalities that we would like to obtain is touch sensing, that with the goal to replace mechanical buttons, and the lighting in order to obtain new aesthetics through ambient lighting. More in detail, for the touch sensing functionality, our aim is to achieve printed on-off buttons on the panel of a car's dashboard, the fascia, that is the part that goes in between the driver and the passenger, is the part that normally you've got there the multimedia controls or air conditioning vents and controls. So our idea is that in the future we see that the touch surfaces will now have buttons or knobs, and in order to have a more stylish and functional interior of the cars. So that's our aim, to achieve printed on-off buttons on this panel. The main features that we want to obtain is that we would like to have the touch sensor and the transductor integrated in the plastic part, in the plastic fascia, and it will be also desirable to integrate the communication as well as power to have the entire functionality. Let's say also that the device must resist the overmolding hard conditions and has to be fully functional after this process. If we go to the lighting, in this case, the goal is to achieve ambient lighting on the panel in the same part, in the car dashboard fascia. And lighting makes us to increase design options and create personal lighting atmosphere in our car. And this is a trend that is right now is ongoing, more and more integration of lighting. So the idea is to have these LEDs embedded in the fascia, so we can, in connection with the aesthetic or the decoration, we can have new lighting decorated parts. Now, in this case also, LED and driver should be integrated in the plastic car, and the communication and power also would be desirable to have integrated. So after these challenges, if we go to the phase 1, what has been done in the LIBET project, let's say, as Zachary said, explained in the first presentation, the technological assessment service is a mandatory service, one of the main points of services that we have in the LIBET. And it's very important due to the evaluation of the technical feasibility, or in our case, for example, the technical feasibility and the risk level of the development that we are going to do. No? If we go more in detail about this feasibility and risk level, one of the first steps was to define the electric and electronic system architecture of what is going to be the scope of the project, what we're going to integrate in the part and what is not going to be integrated in the part. So we have, in this case, we have some LEDs and also some sensing pads. The LEDs are controlled by a driver, and this driver must be controlled or must be connected with the car with a microcontroller and also a power supply. So that will be the functionality of the LEDs, and the sensing. It will be this sensing pads needs a controller, and this controller also must communicate with the car. Well, after analyzing the pros, the advantages and the disadvantages, the scope of the project was defined to go to the until the driver and the controller, including the LEDs and the sensing pads, but taking out of the scope of this phase all the communication and microcontrollers due to feasibility risks. Okay, after this first step, we make a proposal in how we could implement this functionality in the part. You can see this is the picture that the part that was selected to be integrated the sensing and lighting functions, and there were different options of where we could integrate in this part these capacitive sensor buttons and also the lighting. Some technical challenges that were identified during this phase one. I have to say that even the main technical challenges that we see are related to the process for the overmolding process. There were also some challenges that were related to the ink development due to the compatibility of the ink to the materials that we're gonna use for this process. So, but going in detail more in thermoforming, there were some technical challenges in terms of how to do this thermoforming without not causing damage to the sensor and components. Also has to be taken into account that the elevated temperature that we're going to be in the thermoforming will be more than 170 degrees. And also that for this thermoforming phase, the functional inks need to be stretched into a 3D form, but they must be sure of the functionality, or they must assure the functionality of lighting and sensing. And after this step, we will go through the next one would be injection molding. And the main technical challenges were also, again, in the injection molding, the temperature that would be more than 260 degrees with a very high pressure. Also, the accuracy or tolerance of the thermoform part will be a key issue in order not to crash any component and have any failure of the functionality. And one of the final challenge that we see is that the connector must be designed in order to be able then to connect this part to the rest of the car, of the vehicle. Yeah, other service that was used in this phase one was the pattern mapping service, where it allowed us to identify which are the relevant patents and also the competitors that are working on these topics. No, our aim or goal was to with this map or to do a map of technology trends, see which are the solutions and the competitors that of the development that we are proposing in this framework of LeadBet. No, as a result, we had identified and analyzed the high relevant patents and also the similar patents, and the main competitors also were identified. No, there were also other type of information that were very interesting, as for example, in terms of which are the patents that are right now ongoing referred to the printed electronics, and as we can see, the number of patents are increasing quite quick in the last years, and also some very interesting landscape 3D representation of the technology, where we can see the peaks where the patent developing are right now, or the trends, and where are the valleys where there is still a space, let's say, for this patents or for this work in these topics. A summary of phase one result. well, and with the technical feasibility was assured, let's say, with taking into account that the compatibility of the adhesive and inks with polycarbonate was to be taken into account, and also the overmolding process that is not possible to simulate. So there will be some big issues to solve in the next phase. From the economical point of view, we still didn't have enough input data to do a complete analysis of this issue. And as I said, with the patent mapping service, we saw that the competition is still considered to be weak, or there's not too much concurrence right now in this topic. Going to the next phase, the phase 2, that is the phase that we are right now ongoing. The main objective of this phase is to have a fully functional demonstrator that can fulfill all the testing that was defined, also functional and environmental testing. For this phase 2, there was defined with in collaboration with CPI. There was a flow just to a flow we can handle, how we can achieve this functional demonstrator, starting with an alpha design, going ahead with some overmolding tests, and then evaluating the results and making sub loops if it's necessary, depending on the results. But we can evaluate which of the improvements we need, and after, if this design is mature enough, or at least we think that is enough just to go in the next step, then we'll go to a beta design. That will be this final design, where after the testing, the functional and environmental testing will be made, just to assure all the functionality after all the processes that have been made, and then evaluation of the results. So at the end, we can achieve a functional demonstrator. So right now, we have been working on the first part of alpha design, test, and evaluation results, where technical development activities were made for this proof of concept, or this alpha design was created, in terms of design, in terms of film deposition, or the ink deposition on the films, and thermoforming, and also overmolding. A material selection study incorporating substrate and inks was made, and also a concept in 2D and 3D, layout, component, and thermoform profiles, just to have this insert or this 3D film with electronic integrated previous to the overmolding process. And finally, we produce some alpha demonstrators and make overmolding trials. Okay, so I'm going to explain what was the result of this part. As you can see in the picture, there was some these alpha phase films, thermoforming films, that we use for the first overmolding trials, with an objective of having how we can fix them in the injection process, and also see which is the behavior after injection process of the electronic components, if there is some damage or failures in these components or not. How we made this overmolding process: we took this film, we put it on into the tool and hold the film. Then we set the temperature and pressure for the injection, close the tool, start the injection process, or we fill it with the thermoplastic material. After the injection is finished, there is a cooling time, just to cool down to maintain the structural figure, let's say, and then the tool opens and we take the part. And after analyzing the part, after this overmolding phase, we have to say that the results, we had much better results with PMMA material. That was one of the use instead of the PC material. At first B, we didn't have any circuit degradation, so the tracks were okay. And in terms of components, we have different kind of components, and the IC was okay, the resistors were okay, but we had some LEDs displacement problems or displacement issues with these LEDs. going to the results also that we had. That, as I said, polycarbonate parts, the result weren't okay. Due to higher temperature injection, there was some track degradation and film degradation, as you can see in the upper figure, and there were some tracks that were melted or moved. There were some LED displaced due to the injection process, due to the temperature or pressure or flow of the material, and also the connector was embedded, so it was difficult to access, and that's something that needs to be improved. So as a summary of this alpha phase, in this phase 2, I said that right now we are in the evaluation of the results in order to go to the beta design. So this is part of the process that we are going, and we have some big issues or issues just to make this improvement, or to do some improvements, go to do this beta design. And there was some risk and things to identify as to be improved now. So we are right now going in the beta design until the functional demonstrator. So as a final conclusion, as we are still ongoing, and we hope that to reach this final functional demonstrator soon, and that will allow us to present to our customer these new possibilities and functionalities in order to propose them new designs and different type of parts, not only in the first year. No, and Libet has allowed us to explore this new technology in order to see which are the risks and also which are the key points just to be taken into account. So that's all, and thank you very much.
Thank you very much for this presentation, Joseba. If you have any question for Joseba, please just put them into the chat and I will read them up. I have already got one question for you, Joseba. One asking if you thought of using a 3D printer instead of an inkjet molding.
Well, right now, our main focus is to go in this overmolding process because this is one of our core technologies. But this is something that has been discussed inside the Libet project also, that the possibility to use this 3D printing, but not in this scope, but it's something that in the next future we think that it will be the topic that will be, let's say, will be investigated, or at least in the at this point we are focused on overmolding process, not in the 3D printing. And the next question also I see that is how we can plan to solve the connector concept. Okay, that's a bit issue, and right now we are working with CPI, which are the different kind of options. But well, as I can say is that we are working on different options, and most of them are taking out the film, taking out of the tooling, not going into the injection process. Let's say that we will have a longer film or a strip in the film with the connector, not going inside the tooling.
Yes, and there was also explore limit of 3D forms and integrated function. I guess you already mentioned a bit about that.
I don't know what it means with 3D forms. I think that it was with a 3D. I don't know. Of course is if okay, maybe could be, yeah. If we are talking about different kind of 3D forms of the design right now, okay. Yeah, the design right now is nearly flat. Slightly curved. It's not very, and of course that is one of the topics that if you want to go a very 3D, very risky or there is not only in terms of film, also in on tooling design. In tooling design, there is a big issues. We wanted to go first of all to this 2.5D parts, previous to go to 3D directly parts, because we think that still are some risky points in the integration of the film and electronics before going to investigate more in the 3D forms. But of course, there are some concerns or constraints in that not all the 3D forms are allowed to be made with this flexible electronics, but not only for this flexible electronics. We see that most of the concerns or constraints are the same if we go for decorated films, that you cannot go to all the 3D forms. You have some limits or geometry limits. So there will be the next point, just to try to go in more complex, but we thought that it was challenge enough just to go with this functionalities in this part and solve it first.
Sorry. Any other questions? If not, I'll thank you very much, Joseba. And now we have the fourth, but not the very least, end-user case presentation. This one will be given by Rafael Michalczuk from Swarovski, and is about innovation in functional decorative surfaces. Rafael?
Yes, hello to everyone. Hopefully you hear me.
We do.
Okay, great. So I'm going to share my screen quickly. Okay, in a second you should see it. Everything fine, Ina?
Yes. Okay. Thank you.
Cool. Yes, thanks a lot for being here. Swarovski is also one of the test rabbits of the Libet project, and yeah, today we want to report a little bit on our experiences, how we felt in working in the Libet project, and using the opportunity for using all the services that are provided by the Open Innovation Testbed. As already said, we'll focus on innovations here in functional decorative surfaces. My name is Rafael Michalczuk. I'm basically dealing with different types of innovation projects at Swarovski. And yeah, we'll guide you through a few slides here. So first of all, where does our interest in printed electronics come at all from? Yeah, so basically, as you can see here depicted, our company is very much interested always in playing around with light and crystal. The pictures shown here, they come directly from our so-called crystal world, which is, you need to imagine something between a museum and a garden, right here in Austria, close to Innsbruck. And it showcases quite nicely here on the right hand side, for instance, from an event that we call the Light Festival, how we play really with these different effects, turning light into delight, yeah, and using our sparkle of our products. This is really one of the the major topics, I think, also for the Libet, where we are coming from, and a more concrete one that also initiated certain thoughts about like how we could use maybe printed electronics for the benefit of our company, is originating from this the Designers of the Future Award art installation, actually. So together with this young designer, Anjali Srinivasan, in 2016 back, we did an art installation. I will just quickly show you a little bit what it is about. No worries, there's no voice, so should not interrupt. Anjali basically is explaining here the concept, and as you see, we have quite a wavy structure with a lot of crystal on top of it. This crystal, as you see, it might not be very, let's say, classical, and it goes more and more sparkling in the upper part. And the nice thing here is actually that we implemented it this way, that the crystal got a functionality. And the functionality itself was that you really can touch onto the crystal. And as we have seen in the upper part mainly, you can really try to write with your hand on the crystal surface, leaving certain light. Yeah. So basically what this shows is the combination of on the one hand side, really touch interaction on the crystal and lighting up the crystal underneath. And as we have seen that during this exhibition, actually, yeah, that has been shown in different places worldwide. The interest of customers in that was very high. But on the other hand side, also what we have seen that obviously this installation is very, very heavy. Yeah. And it's obviously quite bulky and big, yeah. And what we thought about is to go more really for something lightweight, maybe something smaller, that could be embedded, for instance, in interior design. These were some thoughts where we met also with the Libet project, where we said, okay, the concept of lightweight embedded electronics could actually help us realize new functionalities. Well, I go further. So at the heart of our use case, what sits there is really the touch interaction combined with the visual interaction. All this is based on a technology platform that we internally call the functional crystal technology platform. This has specific crystals that have a specific coating on top as well, or at the bottom, depending on the usage that we apply. And that allow us not only to have a decorative piece of product, but also really integrate some functionality into it. Yeah, and as you see, we thought some further, like, okay, where can we use this kind of concept? Yeah? And we came up with 3 main domains. Yeah, one of which is the most obvious one, maybe, which is still quite close to, say, let's say, our main classical business. Yeah, so fashion and jewelry. You see, coming from the jewelry part with for instance, a ring or maybe a necklace, going into fashion, where we have, for instance, here displayed this color changing crystals on a dress. What comes along with that is also a certain requirement that go into that okay, you need more flexibility, you need maybe more bendability, you need lightweightness, because actually we did some of these tests also with conventional electronics before, and it always was very, very difficult because all of the systems, they tended to be very, very bulky, and this already quite quickly. The other application field, what we see basically also for overall the printed electronic sector is the interior design, and there's an interesting thing is also the lightweightness, and also the bendability, something like a 2.5D effect that you can maybe achieve. It has been discussed now before. Also asking for my own opinion, like how far you can push all these designs from 2D to 3D. We very often internally talk about something like 2.5D. Yeah, that is somehow possible, but you will see that 3D is a topic as well in our case. At least we explore it. And what actually happened during the Libet project also is Swarovski itself started addressing more and more the automotive sector, both exterior and interior parts. In Libet itself, we focus on the interior parts. And yeah, we have created an own business unit that deals with automotive industry. So here even there's quite some relation to the topics that we have seen before. And what we added to the Libet requirements here, additionally on top of all that, we said, okay, we want to explore specifically the transparency of conductive tracks, for instance, to achieve something what is in our minds already for quite some while, to hide electronics. Yeah, so we have developed products before, might have been lighting, might be for wearables, for instance, where we always tried to hide the electronics so that it is not the focal point in our products or in products with other, let's say, B2B customers. And yeah, this is a main kind of guiding line also for our development within the Libet. And the desired functionalities are really a transparent touch interaction that you hardly can see. and a visual output function as that is of interest in order to interact with the user. If we look now into how we structured all that, and we said we have a little bit different angle maybe than the other use cases. We said, okay, very often we work with customers that, who we actually still need to inspire. So very often it is also this way that we do not work end to end on our own, at least for the B2B business, but we also work with designers from other companies, for instance, to inspire them, enable really new stuff, and then move on in collaborations in working with that. And what we have also seen is that very often we need to initiate this kind of new technology push, because let's say certain industries still do not pull enough of it, so that we can really create let's say new applications out of the technologically already possible opportunities. And what we did here, we split it the Libet our Libet use case actually in 3 types of demonstrators that are quite different. The demonstrator 1 is about just a simple touch array. This comes maybe the closest to that interaction that we have seen in this art installation. The second one is the demo 2, which goes more into functionality. So it showcases more that, okay, we can have even more than just lighting interaction and touch. And demo 3 explores something what is close, let's say, to our main business, to jewelry, a demonstrator of a smart ring, actually, that can have also further sensors, for instance, involved, and is prepared by 3D printed electronics, so also by a different production technology. Before we go into the technical details, and I will show you some of the really nice demonstrators that already have resulted from the Libet project, I wanted really to make the point that from the technological and economic services, what was very, very useful for us was a patent mapping service. And I think also, and Joseph before, and probably also others, they explored that really this is very, very useful, and we can just encourage really to use this service. The patent mapping service really provided us with a lot of interesting insights. We had the chance to use 2 different partners that assisted us in carrying this out, DTI and Axia, and what they come up with was really an in-depth analysis of different publication trends, of a regional analysis of where really patents arrive from, how this really looks in terms of a timeline, also where are current potential competitors, maybe partners for further development, what kind of patent groups, families, and keywords are need to be considered. And this was really, really insightful, and this guided us also in making certain next steps. Good. And looking into the demonstrators, the demonstrator cases. First of all, the simple touch array. So in the simple touch array, we are according to the Libet concept, obviously we are served through the single entry point, first of all, the SCP, but then let's say the thing splits down into the involved researching organizations that help us with demonstrators, or actually they provide them very often to us. And one of the first things was that we also thought about certain layouts, as you see scheduled here, for the touch sensor and the LEDs that need to be involved in such a system. And we did simply some let's say feasibility studies in order to find out, okay, which kind of printing technology will we use? Will we use inkjet? Is it sheet-to-sheet printing? What kind of things are useful for us? And we made first demonstrators out of that. As the journey continued there, so we went also then for 4x4 LED matrix here, for instance, and yeah, in this LED array then, in the end, we had also then studies like where we really looked, okay, how could this interaction then with the crystal look like? How good is it lighting up? Can we really showcase this interaction by this LED matrix? And we investigated, or the colleagues from the research institutions, they mainly investigated really strongly the issue of the transparency with silver nanowires. Yes, please.
Oh, well, you just dropped out, but now I can hear you again. Sorry.
Okay, no problem. Maybe some connection issue. Okay, now what you just wanted to explain is that the colleagues went for different approaches in order to achieve this transparency, and they benchmarked themselves against, let's say, available solutions from the market. They benchmarked against the resistivity that is available already there, analyzed in detail, like, okay, what kind of structures we also get in terms of this print, what also has obviously an effect on transparency, visual effect in that sense, and they optimize all the way along to find solutions that suit our use case the best. And what is quite nice really to see here is this effect in the end of what have been achieved so far. So 1 second, I think the whoopala. Okay, now it works. What we see here, or hardly see, or we don't see it actually, is that we have a sheet that is, in the end, we can say transparent, with conductive tracks there that you can't see. But we have the opportunity to embed LEDs there and interact with the crystals. Just take a look. As you see, by touching the crystals that are conductive themselves, we can steer the other crystals that are light up. Yeah. And as we always say, it's quite some magical effect, as you really don't know, first of all, where the LEDs are, where the tracks are, where actually even you need to place the crystal, and then how you interact with it. So we call this the magical effect of demo 1, and we're quite happy with this result. And now we are making our further thoughts, like how to present this to customers, and how to make let's say use of it. But this already has been achieved, and I think it's really a very good result. Moving on for the demonstrator 2, as I said, here we have mainly a multifunctional case. So this means that apart only from the pure, let's say, touch and lighting interaction, we have also certain other other elements that we want to test and showcase here, specifically also for potential customers. You see again here, there was a lot of space for creativity there. We started really drawing by hand. Yeah. Afterwards, we did cut designs. We tested a lot. We did test prints. We characterized with the help of the test bed what we got there. We took it in our lab, did also measurements to verify what we have. Afterwards, we had also let's say first installations, test setups at Swarovski internally. You see this really very let's say provisorical first test setups where we just have explored what we can actually do with all these technologies. And this was also one intermediary step where we just looked into it in these terms. Yeah, okay, what can we put there? How can we interact with the crystal? How can we use one of the crystals to steer maybe the thing? What kind of combinations are possible also from looking from the, let's say, demo board point of view, and what we can achieve there. And as you see, there's already a printed NFC coil on that. We experimented also with a QI charger there, with a temperature sensor, a thermocouple. So much more functionalities will be involved. And also for here, we already started then applying the transparency effect. So you see colleagues here on the lab This is on DTI side, testing. Yeah, exactly. Testing really lab-wise. Okay, how good is the transparency? And you see, it's really actually good. Yes, you can completely see through it. As we did here with measurements. You see even other components. You can see even the other printed components through the through the first component. Yeah, so it's quite nice. We are connecting, disconnecting the LEDs here in this case, just to showcase that this works. Yeah, and I will move on. And as I promised, like, okay, we looked also in other functionalities. And the other functionalities, for instance, is involving NFC for also data interaction, or more, let's say, user interaction. We have a typical NFC demo board. It's a printed NFC coil. We put our crystal on top with a specific coating actually again, and that allows us to transmit the signal. And as you see, with enabled NFC, we land at our Libet page, where hopefully you also will land soon and then apply maybe for your projects. So yeah, this is really nice. The third case, as I promised, this lies quite, let's say, in the sweet spot of our a very typical of interest, let's say in jewelry, but in the direction of a smart jewelry. So actually, it's about the smart ring, and here we work strongly with one of the Libet partners, with TNO. First of all. We tested simply like how to embed our crystals into their 3D materials was one of the first steps. Afterwards, we did test prints with their 3D multi-material palette line. What they have there available also for you test, and you see, okay, one of the first steps was really to to create kind of a test shape with still a board, a classical kind of PCB FF4 board, coupled just to the touch sensitive part, and also, let's say, the electrode that was printed. This just again was a proof of concept, just to show, okay, this works, yeah. And after we have shown, okay, we can use this, we can also achieve here is some 3D print that really is conductive, it has certain properties that are necessary. Then we moved on into the designing a test structure. And in this terms, it is a test structure in form of a ring. As you see, that involves also a crystal. Here we have a little bit a look inside of this classical 3D print. It really reminds us of classical 3D printing with all the supporting structures that are necessary to hold it. And what's the interesting part about this is obviously that the 3D printed tracks, they are already involved in the parts. We have also a proper battery holder for this. There is a LED involved, a touch sensor, and the electronics that we have seen before on the PCB board here is now printed. And let's say the components that can't be printed obviously are assembled and during, let's say, the two-phase printing process within this electronics already, and it serves really to prototype a smart product in a very customizable way, which might be really a benefit of this technology in future, that enables really much more customization. And if you can imagine, let's say a use case like a ring easily indicates why it's useful, mainly maybe for something like that you need a sensor very close, let's say, to skin, for instance, and but you have very different shapes of fingers, for instance, and then actually really to make a close junction there, this technology actually might be very useful. So this is why we are exploring it with our partner TNO, and also here we are very happy to get this support. And as you can imagine, also one of the thoughts behind all this is obviously always that we use this opportunity, as, let's say, our knowledge would not allow us to do this on our own. Yeah? we also need help here from the experts. So there might be already some questions. Oh no, it's Nina writing for questions. Okay, this is what I prepared for you. And I reserved a little bit of time for questions. Yeah, as usually there's no time available, but today I'll try to leave a little bit of time.
Thank you, Abel. I don't know if we have any questions already. I wrote in the chat, but people have a tendency to listen and then write. So give people a few seconds to write in any questions.
No problem. There aren't any. We are also not frustrated. It's also fine.
No, but when are we able to buy this smart ring?
Yeah, we wait for it. I mean, as you see, it is a 3D printing technology, so we need to use its benefits, and they for sure do not lie, let's say, into mass scale at once, because this is not the suitable technology then. But yeah, let's say the latest example for sure is very much really on a feasibility level, going really into exploring what is possible, where we can go, what are the limits, how far we really can go. Let's say in the other use cases, I would believe, or in the other demonstrators, in my opinion, it's a bit closer to market, or even much closer. I would say that something like the touch interaction with the visual indication is already quite close to that we could move into a market with that, also with in cooperation with some let's say suppliers that work already in Ethereum. This is quite realistic, and let's say a timeline even could be, I would say, I mean, the shortest would be probably a year, but as I know, this process is probably, it will take longer, but maybe in 2 years we will see it.
Yeah, nice. I don't think there is any question at the moment, Abel. I think that your presentation was really, really, good and understandable. Is there anyone, please, you can unmute yourself and just ask Abel if you have a question.
I think this is a good example here as of a situation where you try some technology out and see what you can use it for, rather than the other way around, where you have a specific problem and then you want to find a solution for it. So you have let's see what the technology can do, and then try to take the advantage of it. And I think this is how you can do groundbreaking stuff. So I'm pretty sure this is it's an interesting way forward, and a way where you can get some skin around the good ideas that we have in a Libet project like this here. So I love it.
Yeah, we're very happy really with that, and I must say, we let's say in B2B relations, we talk with customers a bit about this outcomes what we have here, and yeah, they already love it. So I think there is potential.
I got one question here, Ravel.
Yes.
Which energy solution are you going for? Battery, solar cell, etc.?
If we need a battery or we need a solar cell here, no.
What kind of energy solution will you go for?
Okay, let's say if we look into a car, we have energy supply. Yeah, usually. So this we can connect to that what the vehicle has. Probably in future it will be, I don't know, electrical or hydrogen cars. So they will provide what is necessary. We explore actually also photovoltaics and batteries in other projects, but not within the Libet project, I must say. And this is simply to the fact that in these use cases, mainly we see that we can cover it either by conventional solutions so far that are, let's say, to be trusted. And the other thing is, that let's say for the interior cases, which is both in home and in car, we simply do not need it.
Okay.
Yeah.
I think that was it for the question. We'll again open for the Wonder session, where you'll also be able to talk with experts. I'll thank everyone for the Zoom part, for taking part. I will very soon close the recording and the Zoom part, but we will continue in the Wonder part. And I will, of course, again put in the link for the Wonder part if you have any questions for the experts in there. And I'd like to thank all the presenters today. Thank you very much for your presentations. I don't know if you have some last word, Javier, before I close the floor.
No, thanks a lot, and yeah, go for Libet. Yeah.
Thank you for
Thank
that.
you.
Yeah. And thanks everybody, and thanks Nina for nice conducting. Really good hosting. Okay. Yeah.
Thank you. And I will post the Wonder session, and I will also post if you want to sign up for a little bit, if you have an idea, please go to our website and sign up, or you can also go to the Wonder session and talk with experts and develop the idea, and then go to the Libet website to sign up for a meeting with us. Thank you.
Thank you. Bye-bye.
Bye.
Thank you.